Hello, my name is Mojan, and today I'll be presenting LiteTransformerSearch, which is a training-free and efficient NAS pipeline for autoregressive transformers. This is a joint work with my co-authors at Microsoft Research. Recent advances in transformers has resulted in a huge increase in the size and complexity of these models. This increase in model size poses several roadblocks in deploying these models on commodity hardware for day-to-day use. As an example, the now relatively old Transformer XL has a latency of 1 second and a peak memory of nearly 1 gigabyte, which cannot be supported in many platforms. Neural architecture search provides a great opportunity to find transformers that have reasonable performance in terms of task-specific metrics like perplexity, while ensuring low hardware costs. Our goal is to use NAS to find models that are on the perplexity versus latency and memory Pareto frontier, shown here with the green dashed line. The NAS pipeline consists of three main components: the search space, the controller, and the evaluator. First, let's take a look at our search space. This figure shows all the free parameters in our search, which includes the number of decoder layers, number of attention heads, decoder output dimension or model dim, inner dimension of the feed-forward network, embedding dimension, and the division factor of the input embedding. We allow each of these parameters to change on a per layer basis, which gives us 10 to the power 54 different heterogeneous transformers in total. The controller conducts the search over this space, and we use genetic algorithms, but essentially any discrete Pareto search algorithm can be used here. For the evaluation, it's straightforward to measure latency and memory of candidate models directly on the hardware. However, measuring perplexity is very challenging, and we need a proxy for it since it is infeasible to train each architecture fully to find the real perplexity. Our hypothesis is that the number of decoder parameters is strongly indicative of perplexity in autoregressive transformers. To validate our hypothesis, we randomly sampled 300 architectures and trained them fully. And these models come from two popularly used autoregressive transformer backbones, which are Transformer XL and GPT-2. We then rank them based on the perplexity that they achieve after full training, and we call this the ground truth ranking, which needs more than 25,000 GPU hours of training. As the proxy ranking, I'm using the number of decoder parameters, and as you can see, the two rankings are highly correlated. And more importantly, the ranking using decoder parameters requires absolutely no training, so we can use it as a proxy for perplexity in the inner loop of our search to rank the architectures. Now let's see if the model topology affects how well the decoder parameter count proxy works. So for a given budget on decoder parameter count, we sampled different architectures that range deep narrow models with over 100 layers to shallow wide models with only 2 layers but model dim of more than 1200. And as you can see, the validation perplexity stays largely the same regardless of the topology as long as the decoder parameter count is fixed. But while perplexity stays the same, the hardware performance metrics like latency and memory can vary greatly from one topology to the next. For example, here the latency changes up to 2.8 times and memory up to 5.5 times for models with the same parameter count and different topology. The second set of proxies are based on some score, which can either be coming from pruning at initialization techniques or using some heuristic proxies developed for CNNs. And for these proxies, we integrated our prior knowledge that the input embedding layer dominates the score, but it does not necessarily correlate with perplexity, so we omit it in the proxies for them to work. Here I'm showing the Spearman rank correlation of these proxies evaluated on 200 random architectures versus their computation cost in terms of flops. The provided methods all perform relatively well, but as you can see, the decoder parameter count, which is highlighted with the green circle, still dominates the remaining proxies with absolutely zero computation cost. And we also compared the Pareto frontier models found by NAS with a scaled version of the backbone architectures, which are essentially the same per layer parameters proposed in the original papers, and we are varying the number of layers between 1 to 16. And as you can see in the low latency regime, our search finds models that have significantly lower perplexity compared to the baseline. And in the higher latency regime, we find models that have the same perplexity as the 16-layer Transformer XL, while achieving between 1.6 to 2.5 times faster runtime and about 2 times lower peak memory across different CPUs and GPUs. And similarly, for the GPT-2 backbone, we find models that are between 1.3 to 1.6 times faster and consume about 1.2 times less memory, but achieve the same perplexity as the GPT-2 base architecture. So in summary, we empirically established a strong correlation between the number of decoder parameters and final model performance for autoregressive transformers. And we develop an efficient on-device search that finds models on the Pareto frontier of perplexity versus various hardware costs without need for any training. And our search finishes in under 3 hours on a commodity laptop. We also provide large-scale proof-of-concept experiments on the effectiveness of decoder parameter count as a ranking proxy using over 2,800 autoregressive models of varying size, backbones, and 2 large language datasets.